The next great gold rush isn't on Earth. It's happening right now, 240,000 miles away, in a place of stunning, brutal extremes. A place of eternal darkness, so cold it rivals the surface of Pluto, where sunlight hasn't struck for billions of years. This isn't science fiction. Half a century after we last left footprints on the moon, a new, far more complicated race is on. This time, it's not for flags and footprints. It's for power, profit, and a resource that could define humanity's future in the cosmos. Major powers, particularly the United States and China, are quietly competing to reach the darkest places on the moon.
The directive I'm signing today will refocus America's space program on human exploration and discovery.
中国无意和任何国家搞太空竞赛，我们也不谋求所谓的太空优势。
We cannot lose the moon and lose the race to the moon to China.
If we fall behind, if we make a mistake, we may never catch up, and the consequences could shift the balance of power here on Earth.
What priceless secret could be hidden within this darkness? What might be lurking in the moon's most dangerous place? Why are nations and private companies in a high-stakes competition to claim the most treacherous and valuable real estate in the solar system, the moon's south pole? They're racing to its deep, permanently shadowed craters. And it's not for some sci-fi fantasy about the dark side of the moon, which is really just the far side we don't see. No, this is all about the shadows. Because hidden in that perpetual, cryogenic night is something more valuable than gold. In the next few minutes, we'll lift the veil of mystery over the moon's permanently shadowed regions. For most of history, the moon was a thing of wonder. Then, for a brilliant moment in the 20th century, it became a destination. The Apollo program was a staggering achievement, a monument to human genius fueled by the Cold War. It was a geopolitical showdown, the Soviets versus the Americans, a race to prove who had the superior technology, the superior system. When Neil Armstrong took that one small step, America had won. But after Apollo 17 came home in 1972, something strange happened. We stopped sending people. For over 50 years, humanity's ambitions shifted closer to home, to low Earth orbit, the Space Shuttle, and the International Space Station. The moon went back to being that silent, silver disk in the night sky. The cost was too high, the political will had evaporated, and besides, we'd already been there. The question was, why go back? Well, the world has changed. The old space race was a two-horse competition. Today's is a global scramble with a dozen nations and a new breed of billionaire-backed companies. And they aren't aiming for the familiar dusty plains of the Apollo missions. They're all headed for the same spot, the South Pole. So, what changed? Why, after half a century of quiet, is everyone suddenly racing back to the most dangerous place on the moon? The answer isn't about what we can bring back to Earth, but what we find and use up there. Welcome to Cosmic Chronicles. We have noticed that 91% of you that watch this channel frequently do not subscribe. If you've ever enjoyed my video, please could you do me a favor and hit the subscribe button. It helps this channel more than you know, and the bigger the channel gets, the more valuable content you enjoy. The lunar South Pole is unlike any environment we've ever tried to operate in. It's a landscape of brutal contrasts. While the rims of some craters are bathed in near-constant sunlight, earning them the nickname Peaks of Eternal Light, the floors of those same craters are plunged into eternal darkness. These are the permanently shadowed regions, or PSRs. They exist because the moon is barely tilted on its axis, just 1.5 degrees. Earth's 23.5 degree tilt gives us seasons. The moon's tiny wobble means that at the poles, the sun's rays just skim the surface. For the deepest craters, this means their floors haven't seen a direct ray of sunlight in, potentially, billions of years. In that eternal night, the cold is absolute. temperatures can plummet to as low as negative 248 degrees Celsius, or about 25 Kelvin. That's so cold it rivals the iciest spots on Pluto, making these craters some of the coldest measured solid surfaces in our solar system. An environment that extreme is an engineer's nightmare. It can make steel brittle as glass, freeze lubricants solid, and kill batteries in a heartbeat. The terrain itself is a mess of rugged, poorly mapped craters shrouded in darkness. Landing there requires insane precision. And if you land at the bottom of a deep crater, its walls can block your line of sight to Earth, cutting you off completely without a network of relay satellites. Then there's the dust. Lunar regolith isn't like beach sand. It's a fine powder of microscopic, razor-sharp shards of glass and rock. It's electrostatically charged, so it clings to everything: visors, seals, solar panels, you name it. For a long-term base, it's a mission-ending threat. So why risk so much to go to this hostile, frozen, dark, and dangerous place? Because that unforgiving environment creates the perfect cosmic trap. For eons, these permanently shadowed craters have acted as cosmic cold traps. Any water that found its way in, from comets or asteroids, was frozen solid, locked away from the sun's radiation. The most important of these frozen volatiles is water ice. Why is water such a big deal in space? Not just for drinking. Its true value is as the bedrock of an off-world economy. With enough energy, which is plentiful on those sunlit crater rims, you can split water, H2O, into its components, hydrogen and oxygen. Oxygen is breathable air, and liquid hydrogen and liquid oxygen happen to be one of the most efficient and powerful rocket propellants we use. Suddenly, the moon isn't just a rock to visit, it's an interplanetary gas station. A lunar base with access to water could produce its own air and its own rocket fuel. This shatters the greatest constraint of space exploration, the tyranny of the launch equation. Right now, up to 90% of a massive rocket's weight is just the fuel it needs to get off Earth. If you can refuel in space, you can launch missions to Mars from the moon, making them cheaper and more efficient. Lunar water is a force multiplier for exploring the entire solar system. But how do we know it's there? The discovery was a slow-burn detective story. It started with hints from probes like Clementine in 1994 and Lunar Prospector in 1998, which found hydrogen at the poles, a telltale sign of water. Then, in 2008, India's Chandrayaan-1 orbiter gave us the first direct mineralogical proof. The smoking gun came in 2009 with NASA's LCROSS mission. NASA deliberately crashed a projectile into Cabeus Crater, a PSR at the South Pole, and a second spacecraft flew through the plume of debris. The results were clear: significant amounts of water ice. Later missions, like NASA's Lunar Reconnaissance Orbiter and the Sophia Observatory, have confirmed that water is widespread. The mystery is no longer if there is water. The trillion-dollar questions are: how much is there? What form is it in? And how hard is it to get? That's the race that's happening right now. Unlike the Cold War, this new lunar race is a global affair with many powerful players. On one side, you have the United States and its Artemis program. The goal is to build the first long-term human presence on the moon. The first crewed flight, Artemis II, will be a lunar flyby. Artemis III is slated to be the historic return, aiming for the first crewed landing near the South Pole later this decade. This new American strategy relies heavily on commercial partners like SpaceX and Blue Origin to build the landers. This is all organized under the Artemis Accords, a set of principles for lunar exploration that has been signed by over 40 countries, creating a US-led bloc. But there is a major competitor: China. The Chinese lunar exploration program, Chang'e, has been a masterclass in methodical success. In 2019, Chang'e 4 made the first ever soft landing on the far side of the moon. In 2020, Chang'e 5 brought back lunar samples. Most recently, Chang'e 6 returned the first ever samples from the moon's far side. China is open about its goals. It aims to land its own astronauts, or taikonauts, on the moon by 2030, and is partnering with Russia to build the International Lunar Research Station, ILRS, at the South Pole. This creates a direct alternative to the Artemis Alliance. And it's not just a two-nation race. India made history in 2023 when its Chandrayaan-3 mission became the first to soft land in the lunar South Polar region. Japan recently pulled off an incredible pinpoint landing with its SLIM spacecraft. These nations, along with Europe, the UAE, and others, are all staking their own claims, sometimes partnering with the US, sometimes with China, and often pursuing their own goals. This isn't just a race, it's a geopolitical realignment where 21st century power could be defined by infrastructure on the moon. Knowing water is there is one thing. Actually mining it is another challenge entirely. The ice isn't a neat skating rink. It's likely mixed in with the soil in low concentrations, maybe just a few %, and buried under more dirt. Getting it out will require a whole new generation of technology. Robotic miners that can work in cryogenic darkness, drills that can pierce frozen ground, and processing plants to heat the soil and capture the water vapor. This was the goal of missions in NASA's Commercial Lunar Payload Services (CLPS) initiative. One of the key projects was the Viper rover, a golf cart-sized robot designed to map water ice deposits by drilling into the PSRs. However, demonstrating just how difficult and expensive this is, the mission was canceled in 2024 due to rising costs. The fundamental need for a water-hunting rover remains critical, but a mission like VIPER is currently off the table. China's upcoming Chang'e 7 and Chang'e 8 missions have similar goals, scouting for resources and testing the tech needed to use them. This technological challenge is shadowed by a legal one. Who owns this stuff? The Outer Space Treaty of 1967 says no nation can claim a celestial body. You can't plant a flag and own a crater. But the treaty is fuzzy on resource extraction. The Artemis Accords try to create a framework for this, but Russia and China haven't signed on. This legal gray area adds another layer of tension. The first entity to successfully mine lunar water won't just gain a massive advantage, it could set a powerful precedent that shapes space law for centuries. This new space race, the rush for lunar water, and the dawn of a true spacefaring economy is a story being written right now by rovers, landers, and soon, by people. The technology, politics, and economics are all shifting faster than ever. If you want to follow along to see who succeeds, who fails, and what it all means for our future, make sure you subscribe and hit the bell for more deep dives into humanity's next great chapter. We are watching a fundamental pivot in human history. This return to the moon isn't a repeat of Apollo, it's the start of something new. It's a race driven less by ideology and more by economics and strategic advantage. The goal is no longer a fleeting visit, but a permanent foothold. The desolate, frozen craters of the lunar South Pole are poised to become the most important industrial zone beyond Earth. The nation or company that unlocks that frozen water won't just win a race. They will hold the key to a sustainable human presence on the moon, to missions to Mars, and to a future that is, for now, just on the edge of our imagination. The question is no longer if we will build a future on the moon, but who will build it.